So you wonder why I have this subtitle. You're wondering, Bond is now doing gray screens, which is not what I'm known for. So you will decide whether I'm a gray screen being and old and gray and in the way, maybe all three of those things. Here at this meeting, I thought, okay, Inasto's a little bit older, but then I remembered that Brent is probably a smidgen older, and then it may well be that I'm in the next rank order. Anyway, so here we go. Well, I hope you will come away and stay and say, no, he's still colorful, if continuing to be mystifying. So this had to be, right? At CITA, I did a little talk, and I can spend hours on this because it encodes everything that's sort of in my mind about physics. Rest assured, I'm not going to make you see all aspects of this. I have had a very long history with KITP. I was here when it was ITP, and here before it actually formally got started. My talk then was entropy, neutrinos, and supernova, emphasis on entropy and shocking matters. In the audience was Hans Bethe, a non-trivial being who was giving me critique afterwards in a good way. And 2020 was the last talk I gave here, and then pandemic hit. And so playing on that, I did entropy, phonons, and phase transitions in stochastic inflation during and after. And why is that relevant here? It's because one of our themes will be, not just me, but Nate Carlson, who's speaking next, is primordial non-Gaussianity and how we can detect it. I won't try and give you all the definitions. He'll introduce zeta, which is essentially an entropy variable, in more detail. All the fluctuations that give rise to us in the room, as you may not know, are actually entropy fluctuations that condensed out in the ultra-early universe. If I were thinking of a title that would be riffing off of this, it would be Entropy, the Cosmic Web, and Entropic Emissions and Absorptions, as we introduced the terminology lim-lam, playing off of flim-flam, but it is a very serious subject which has a tremendous future. I won't go through this. These are the topics that were there in 2020. You probably wouldn't notice that that's what I did anyway. But underlying almost everything I do is the same thing that the great Johnny Wheeler came to, is that everything is information, thus entropy, thus transport of entropy, thus entropic emissions. And it is a really interesting thing to think of the universe in those ways. Okay, so let's go back to the theme of old and gray and in the way. I would say, or perhaps the last few. So Bond is bound to the universe, all in our interconnected cosmic web, entangled as we are in the universal web, the superweb. I would maybe even call it the super duper web. But I had this in my title, Superweb, so I have to give an idea of what I mean by that. So we're celebrating here and now once again in 2023. And what you may not know is the concept cosmic web actually began here in an office just over there with some very good friends, B, K, and P. And because K, or P, Pagasian, is highlighted, he owes me many minutes on this talk. But I'm going to make a couple of points here. The wedding, or shall I say wedding, of east-west ideas that became the ideas of the cosmic web. And I have to invoke the K of B, K, and P, our very good friend Lev Kaufman. And the unification of East and West ideas is because we embraced, I embraced anyway, the language of the Russians, which was deformation tensors, also known as tribines, and so therefore they're intimately related to the full general relativistic gravity. And they're the exponent of them is the strain, which anybody who's read my papers knows that I am always under strain and like to talk about it. They're also called tides. But the key feature that I think we added to the game that wasn't added before is that you should understand these things in terms of an RG flow. RG flow means that you're changing scale, but you aren't dealing with specific filtering scales. You've got a whole hierarchy of scales. So in scale space, this is our ADS C FT with an R random, C cosmic, because it is not conformal, because it's broken by the nature of the power spectrum, which is not a power law. Okay, so I'm going to riff a bit more on that history. Well, first of all, I hope you do not get gastrophysical indigestion from hearing me, but that could happen. So I want to say cheers to the forever young Inasto, and the soon to arrive, who I can almost wave to there, Sergei Shendarin. And I'm going to go back to a time in Crete. Nick was with me. In a Greek taverna, that's where I first met Shendarin. And I was one of the rare people in the West that had actually really tuned into the Zoldovich school and those ideas. In the West, most people only saw spherical cows when they looked at the universe, and did not even, maybe Brent was different because there were a few people that had a little bit of supercluster idea, but when Peebles looked at his famous map, he said, it's just what your eyes are doing, they're joining stuff together. So it was a really big deal to emerge the interconnected cosmic web, and so we did. Going back to this for a second, just to remind you that I do like color, multiple fonts, and all of that. We're going to start with a few examples. First of all, I am going to read this comment. We have a toolkit for CMB and LSS experiments, creating Websky ensembles. Ski is, even though it should be Websky, and that's what everybody says, but I like the Websky, the concept that we are skiing the universe and testing beyond the standard models of cosmology theories. And the methodology, it does not have to be mass peak patches, but it happens to be an extremely rapid and efficient code. And, you can also do, obviously, this with n-body halos, et cetera. But you need hydro, and as Nate will talk about, early universe simulations, and a coarse-grained picture of halo and the field beyond halos. That's sort of an essential ingredient. And in order to actually turn those into the maps, like we just saw, whole sequence, you need a fine-grained stochastic response function. What is never done is taking really the stochasticity into account, and yet it's absolutely essential. So what I'm talking about, we used to term painting on. You have a halo and you take your brush of multicolors and you paint it on, and that's how you make the maps. And it's basically that way, but there is a lot of work that needs to be done in the subject, and certainly we're trying to do it at CITA in order to determine response functions. You can do some of this from using data, but you can also try, if you believe them, use hydrodynamical simulations, and we are playing both games at CITA and with various people who have been through CITA. Response functions is a language which I would like people to start using. I also used susceptibilities, Fourier transform, form factors. The word that should have been abolished from the literature right at the beginning is that stupid word bias. Hi, Nick. Okay, and so I think you all know these acronyms, BBKS, BCK, did a whole bunch of work with Steve Myers, And then in '96, we did Cosmic Web, but using these ideas and the tidal tensor to define how the filaments, the membranes, and the voids arose. And it's a very successful theory. Then we applied it everywhere. But it is a real mini industry at CITA with lots of people engaged. And I'm not going to be able to go over everybody's thing. I'm just going to pull a few things out of the hat to talk about today. But you heard from Dong Wu on line intensity mapping and the applications of some of these methods to that. And you're going to hear from Nate Carlson, and then in a little while we'll be joined by Martine Loken. Anyway, there are lots of people that are doing various things with me, and I'm going to also highlight some things that I did with an undergraduate who's now a graduate student at UPenn. Okay, so the first thing I'm going to do is say what is the status of peak patches, because if you don't think it works, then everything that I would say would have no meaning, but in fact it works really well. It's the explanation of bias is totally perfect, and there's an analytic theory that's totally perfect, which most people don't know about, probably because I didn't really publish it. No, it's actually buried in the Bonner-Myers papers, but only the aficionados would have dug so deep. It works very well compared to n-body simulations and peak patch simulations, as well as the analytics. And there is a brilliant overlap of peak patch halos with n-body halos. And so there's only the odd outliers, so it's pretty good. We did a whole bunch of tests for Euclid when I was playing the Euclid game, which I sort of still am in a way, in power, correlation functions, and other things. And it also works, but not perfectly, for higher order statistics, but we used it for higher order statistics. But a major point, and in the original Bonner-Myers paper, we had a whole tiling of the universe in cells. But then I did what I thought was a clever thing. It was to put in long wavelengths that coherently tied all of the cells together so the large-scale structures could be obtained really, really well. Then my collaborators, Stein and Alvarez, they're big box people. I would like to warn people not to do big boxes all the time. It's not so great. But if you don't use cells and you try and do a really super duper large calculation, then you will end up, at least in the current version of peak patches, you'll end up missing a lot of halos that are really small. But does that matter? Depends what your probe is. And what I'm going to talk about and why we built this new machine is because H1 is ubiquitous. Seriously? Anyway, so if you look at this region here and you tune in and you tune in, you see the things that are in orange here are the ones that are captured if you did one really large box, if you use 16 tiles in that case, look at how many you get, and so it's actually really rather significant. This kind of dynamic range you're not going to see in any gas dynamical simulation or n-body simulation. It's just not feasible. Peak patches is perfectly suited for light cones. In fact, you can do the gradients of redshift across the cells, which is not so easy to do if you're using n-bodies or gas dynamical sims. I mentioned that H1 needs hierarchical multigrid if you're going to do it well, and you want huge sky at the same time. So now we have what is more or less perfect cell coherence using something that is called music, is what we actually implemented it on, and it was done in a rather clever way. Okay, so I've gone through a whole bunch of the people. I'm going to very quick, oh yeah, I want to say one thing, partly because I like the name. I was in China for a meeting. We used to hold entire meetings that were dedicated to cross-correlation. And then cross-correlations are so ubiquitous, nobody would even consider making a meeting on cross-correlation, except some people in Kyoto of something that's coming up. But because it was in China and Confucius was beaming down on me, I called it Mocking Heaven, because we're doing mocks. Anyway, it was the way things used to be. Cross-correlation used to be novel, and now nobody ever thinks of not doing it. But one of the things you can do, not surprisingly, with the whole peak patch Websky methodology is develop and use novel statistical methods which you can apply to data. Of course, there's the usual cross powers and all of that you're all very familiar with. One of the things we really like at CITA, or at least I do, is oriented stacks where you're basically using either the large-scale tidal tensor, strain tensor, or the Hessian of the density, or better yet, the log of the density, if Ishvan is still here, yes. Anyway, and then what you can do is there's a further degree of freedom after the orientation, so that you can break parity and make these really interesting maps that basically can be decomposed, if it's 2D, into m equals 0, 2, 4. 4 is an indicator of nonlinearity, nonlinear dynamics, and m equals 1 and 3. So just to give an example, this is a standard stack. It was one of the cases we did a while ago. That's all part of the things that Martina is going to talk about in more detail. If you do a spherical stack, you get something like this. This had 800 and something or other clusters. But if you do one of these neat methods, the stack looks like this. And so the idea is that if, for example, you're a cluster and you want to find what is the supercluster environment in a ensemble kind of way, then you would not just do some kind of orientation according to the density of galaxies in the medium on large scales, but you would also say, yeah, but there are more here than there are there. And so you can build these interesting maps. You can then decompose them in this multipole way, and you get, instead of just a radial profile, you get a whole bunch of radial profiles. It is really useful. And the other thing is that if you do that, you can get rid of a lot of the noise properties. So we've had a lot of fun with it, or at least I have. I don't know if the students have, but they certainly have worked on it. Oh, all right, what else have we got here? Okay, that's one thing. The other thing that we played around with, mostly on the interstellar medium and dust so far, is doing stacking on what are called key coals. These are prominent saddles. And of course, Christoph extolled the virtues of saddles as the way to go after filaments. Not necessarily so great because you got to bend them down because filaments are almost never straight. Anyway, so that's kind of neat. I should have put a picture here. The picture not of the key coal stacking, which is really beautiful, but the thing to bear in mind is Mauna Kea, Mauna Loa, and in between is a key coal, and it's called key because it's important. And you measure the prominence of peaks like Mauna Kea and Mauna Loa by the height above the key coal. So finding key coals is non-trivial with galaxy data, but not impossible. And so it's a very interesting thing to stack on that tells you a lot about the cosmic web if you can interpret it properly. Okay, anyway, stacks, stacks, and stacks. You can take the correlation functions, which is actually what stacks are, but you can also take two of them and do an inverse of one of them, and that gives you at least a good approximation to the response functions that are so fundamental to this entire operation. There's all sorts of other things. I don't know if I'll be able to get to it, but the other thing that we're into that we've applied to the CIB, lensed and unlensed, is relative entropy of PDFs. and breaking it up into what are in effect needlets. And it's a really neat method, and we can do higher order correlations without any cost, basically, whereas most people are spending much of their lives building these codes, even to do 3-point for galaxy surveys. Non-Gaussianity is one of our key things, and Nate's going to deal with that. Okay, I'm going to very quickly show you some ways that we can do simple applications. I decided to pull out of my bag of tricks things that even Dongwu might not have seen, and we want to encode in our general peaks to maps kind of code. And so this is, look at that stupid stuff. This is what happens if you take a line of sight through peak patch sim, and you get, in the first instance, if you're passing through halos, you get saturated Lyman alpha absorption. So these are the kind of galaxies you get through, but you can do dwarf galaxies in the same way, so that all of the issues of Lyman alpha of the dwarflets along filaments, it can all be taken into account. You can also do H-alpha emission and all of that, so you can relate to the way people get redshifts, et cetera. But the other interesting thing is, you know, there's a response function for this, is you can simulate the forest by a response function, which is based upon the dark matter density with getting the NH1 in response to that. And there's enough of a exploration of this. This wasn't from me. I thought I had, yeah, Lee et al. 2014. I think it needs to be improved, and you get the forest done really well. And over arbitrarily large scales, this is a redshift 2.4 to 3.1, but you can do it arbitrarily far. And then the other great thing about this with peak patches is you can put ionizing sources that give you that famous QSO N-gamma UV proximity effect that causes things to go down. And so all of those things can all be brought in at the level of lines. There are lots of information here because the velocities are all known from the peak patch simulations. Okay, I think I just wanted to splash some color to wake you up. Okay, so this, let's see. Oh, come on, play. Oh yeah, okay, so this is a bunch of galaxies sweeping through. HOD is used to do the galaxies through redshift. You can see it. This is related to the line intensity mapping. This for H1. The resolution here is higher than the H1 limb experiments. Oh, it stopped. Because, well, just because we wanted to show it related to the galaxies. The actual size of the chine beam, for example, is of order of degrees, so it's fuzzed this out, but you can still do large-scale structure with it, and in fact, you can use it to go for non-Gaussianity. It does a large portion of the sky. Over here is the CIB that accompanies it. I think if I press this one, if I can find it, then the other one says, I shall go too, because I don't want to be left alone. So where is it? Let's try this. Anyway, I wanted to do this one. So this is the CIB as one's propagating. The development of the CIB is associated with these galaxies as you're propagating in redshift. The timing isn't absolutely perfect here. But, you know, you see, isn't it rich from the point of view of the problem with the CIB, of course, is that we don't have tomography. We don't have the redshift relation. So you got to do cross correlations if you're going to try and draw that out, and of course one does. Anyway, apart from what we're using right now for these response functions, we're now trying to measure them in the fire hydrosims that have various high res, and we're going to actually do a number of new versions of that in order to explicitly go after response functions, which are fundamental for this game. So it works. Here's in these way I think I was describing it in terms of putting in all of these bands in L space, for example. This is Planck data. This is peak patches. This is skewness, so we're at the 3-point level. We don't have a 4-point for the CIB at this stage. Nobody's bothered to do it. Why not? Especially if you use the methods we're using, but that's the way of the world. Anyway, so it's interesting, and the CIB will become even more interesting because Simon's Observatory, and especially CITA is going to be able to really go after it because it's got a frequency range, which is going to be quite good. So the topic that I probably will end on, unfortunately, is the lensing of the CIB. And the way we're doing this, all of the signals have to be lensed. Otherwise, because the universe lenses, but nobody lenses very much. And so the way we do it is do a whole bunch of slices and a whole bunch of lensing convergent slices, and one of these slices has a whole bunch of slices in lensing in front of it, and it moves things around, and we think we did this in a very, well, I think we did it in a very clever way. The paper's going to come out very, very soon. It's supposed to have come out a long time ago. But it has magnification as well as what is in effect movement of the pixels in order to take into account the lensing. And the magnification is actually extremely important to take into account. Does that surprise you? No, of course not. But anyway, so we've done a lot of interesting statistics with this. This is just showing the CIB as it develops, the lensing kernels that are in front of it, and the, anyway, you don't want to hear about the root mean square deflection. So an aspect of this is novel methods of going after the data, and I mentioned the needlet L-banded maps that we've made. And the interesting thing is if you go into relative entropy, you can do appropriate differencing, and you can find shapes in the PDFs that you could then go into the PDFs and try and get amplitudes for them. This is an example for lensing, but you can also do the same thing for all of the basic parameters that are going and characterizing the CIB model. In other words, you can use PDF to incrementally improve your models, which has not really been done, but I think it's a really neat method, and we have to exploit it. Okay, I am going to be handing off to Nate. So beyond the standard model physics, so the only thing to do is to end with a movie, which is, these are Gaussian conditions for something that was CO, so line intensity mapping, a map going through frequency. The idea was that we were trying to relate it to CO map, which we're heavily engaged in CITA. But instead of showing the non-Gaussian things, and Nate will be showing more of these, this is showing differences to show different varieties of non-Gaussianity and what it is that one has to do in order to dig these out of something that may have started as Gaussian or not Gaussian. And so we need to find templates that are basically finding these differences. And that means that you're doing needle in a haystack kind of work. But I think there is a whole future of this. It basically involves component separation. So I'm going to end on this. Again, at least I've got two colors in this and a few others. So I am trying to convince you that I'm not as gray, although old and in the way perhaps, as I began the talk with. So this is a summary of different aspects of peak patches, and Nate is going to be talking about the non-Gaussian imprint as one transports from the primordial non-Gaussianity through to making all of these maps, which are all intercorrelated with each other. Not bad.
Well, at least I didn't have to use all my weaponry, right? So, but we have 30 seconds for the questions. and the rest will come at the cost of Nathan.
Thanks. noticed one of the interesting results you show on the kind of new way of stacking where you go beyond the isotropic. And I wonder, can you elaborate a bit more what sort of extra information you were able to extract from the kind of the second map where?
Well, for example, we've done stacking of the Compton Y map from ACT, actually it's ACT plus Planck, on DES galaxies and what are in effect clusters that were found using a kind of clustering method. And the m equals 0 is kind of sharply going down. It's defining things, but the m equals 2 and beyond are actually feeling quite large structure. And the way we did it, which I think is also a novel thing to do, is, you know, you're trying to do things instead of what some people have done, is to take two clusters and say, this cluster is near this cluster, so there will be a bridge in between, and then they try and do a straight line bridgey thing, right? This methodology is, I think, very good because you can have the point process being the cluster, but the information that you're making the catalog of the points that you're going to stack on has a very broad range of possible information. So, for example, we constrain orientations and other things based upon information that might be as far as 20 megaparsecs away, which means that we're feeling superclusters. And that was one of the reasons for developing this. I love superclusters. We sort of might have somewhat pulled the rug out from under superclusters by saying interconnected cosmic web, and therefore, what is a supercluster? But we have one of the great namers of, two great namers of superclusters sitting there. They're up part of the old and gray group. Well, not so gray. But anyway, yeah, there's this whole history, and it's a really interesting thing to do. And you don't just do it for TSAT or something like that. You can do it anywhere. And in particular, I think it's extremely useful to try and get it after clustering information at high redshift. For example, you can use it with line intensity mapping, et cetera. So anyway, of course, because I did it, I think it's got a great future.
Thanks.
Nathan, can you more questions? I have one question, but it's a technical one. Dick, your colorful plot, was it a copy of Transparency, or you actually made it for this talk? The most colorful one.
I haven't been doing transparencies in a long time, Dimitri.
But
However, when I first did it, I made copies of the transparencies, and my electronic form had those things. And
that's what they were referring.
You know, I know you remember the old days.
All right, let's thank Dick once again.